Okay, so we've been working with those equations, haven't we? You get an equation and then you plug it in, right? Okay. All right. Well, let's get started. We left off in chapter 10 talking about root mean square speed, right? And the reason why we want root mean square speed is because it relates to, what did we say? Kinetic energy, right? And remember how we talked about the kinetic molecular theory? And all the assumptions we made about the particles and how they don't have volume. Well, they do, but we consider it negligible. They're moving really fast. Attractions are negligible. Elastic collisions. Okay, so we talked about that, right? Okay, so kinetic energy is related to the root mean square speed, which we said we can abbreviate RMS or U. So let's put that up here. Kinetic energy is 1/2, what do you guys know the equation? Mass times velocity squared. Okay. Okay, let's do this one again. Okay, so I'm going to have two gases at the same temperature. They're sitting in the same room, so they're at the same temperature, right? Well, if they're the same temperature, then aren't they going to have the same kinetic energy? Okay, so I'm going to have gas 1 with the velocity 1, gas 2 with the velocity 2. Okay, so the two gases, are you ready? Okay. Okay, two gases, same temperature, same kinetic energy. One gas is going to be very heavy molar mass. The other gas is going to be very light. Well, if they're at the same temperature, then they're going to have the same kinetic energy, right? So that means I can set these equal to each other. 1/2 m1 u1 squared equals 1/2 m2 u2 squared. Okay, so they have, this is a heavy mass. Mass 1, we'll say, is very heavy. Mass 2 is very light. Can the speeds be the same? No, they can't, right? So if you have a heavy particle, what has to happen to its speed? It's going to be very light compared to the light particle, which is going to be moving very fast. Okay, so think of it this way. A heavy particle is going to be moving very slowly. Okay, so a heavy particle is moving very slowly, and a light particle is going to be moving very fast. Okay, so light particle is moving really fast, big particle moving very slowly. So the heavier the particle, the slower it moves, right? And we can see that if we take a look at their different speeds. Now remember, they're all not traveling at the same speed, but the lighter it is, what did we say? The lighter the particle, what does it do? Faster. The heavier the particle? Slower. Exactly. So as you think about that, we've got our kinetic molecular theory that we talked about. We've got root mean square speed that we've talked about, and you've got these particles. Okay, so each ball represents an atom. Okay, bigger the ball, the bigger the mass. So thinking about those things that we've talked about, our kinetic molecular theory, root mean square speed, decide which of these, if they're all at the same temperature, which of these containers is going to feel the greatest pressure. So think about it. What do you guys think? Some say A, some say C, most like C's. B? What do we think? B, perhaps? The greatest pressure? Yes, the container. What's it going to feel the greatest pressure? A, B, or C? What do we think?
Slower is faster, which means more pressure.
Okay, so the lighter it is, the faster it's moving, yes? Okay, does that really mean more pressure, though? And the heavier it is, the slower it moves.
Didn't we discuss that yesterday? I mean, sorry.
Yeah, we are, yeah. So,
Tuesday?
they all blend together. What do you think? Yeah, because you're light, and you could be going really fast into your garage door, right? Or your car, which is a lot heavier, could be going very slowly to the garage door. So, yeah, so that's not necessarily going to dent that too much, is it? Okay, so what are we thinking? Yeah, actually, some of us think B, some think C. None of the above. It cannot be determined. Yeah, well, actually, the correct answer, we're going to go with C. C. Oh, wow. Okay, how come? There's more of them. So how many times is the container going to feel being hit? That would be pressure, right? A lot more, therefore more pressure. What about A and B? A, not so many, B, not so many. Well, some particles move faster, true, and some move slower, but their mass is lighter. So they're not going to have as much force, okay, because they are a lighter mass. Now, the bigger particle has more mass, but it's moving slower. Again, not as much force. So actually, the answer is C for that one. Okay, now as we talk about our root mean square speed, we have to also talk about how we're going to calculate root mean square speed. How do we calculate that? Okay, so U is equal to the square root of 3 RT. Now, do you remember this symbol? What does this symbol mean? Molar mass, right? Okay. Now, R is a gas law constant. But we're going to have different units this time. Remember how we were talking about, oh, we're going to focus on 2 different values of R? Well, the 0.8026 liters atmosphere mole Kelvin, that's with the ideal gas law. This one, since we're talking about energy and joules, we're going to be using the 8.314 joules per mole Kelvin. Okay? Now, I'm going to rewrite the joules into kilogram meter squared per second squared, because that means the same thing. So let's say 8.314 kilogram meter squared per second squared mole Kelvin. Now let's think about how the units are matching up. Well, I've got Kelvin over here, so guess what temperature has to be in? Kelvin. Okay, so that would cancel the kelvins. Now I've got molar mass. What are the units of molar mass? Grams per mole. Do I have grams per mole? No. What do I have? Kilograms per mole. So guess what you have to do? That's right. You're going to have to change the molar mass to units of kilogram per mole. Now when you do that, these cancel, and you're left with meter squared per second squared. And what if you take the square root of that? What do you get? Meters per second. So my speed comes out to be in units of meters per second. And you do have to change that to kilograms per mole. You have to change molar mass to kilograms per mole. So let's see if you can calculate that. Let's see if you can calculate the root mean square speed for neon. So we're going to do neon gas. And let's say it's at 298 Kelvin. Okay, so tell me what the root mean square speed for neon gas at 298 degrees Kelvin. Okay, so you do have to change that molar mass, right? Gosh, how do we change that molar mass? It's grams per mole. How do we change it to kilograms per mole? Because you divide By 1,000. So you're going to move it to the left. So everybody can convert the grams per mole to kilograms per mole. Everybody got that? Okay, so you're plugging it in, cranking out those numbers. These are, yeah, but we're just doing neon right now. We'll talk about those other gases in a minute. For neon?
No.
Yes, that's right, 607. Okay, so did we get it? No? You know what that is? What's the molar mass of neon? Isn't that molar mass there? Okay, so where do you get molar mass from? Periodic table. So you look up neon, right? And you do have to change that to kilograms. You're off by your decimals. Somehow your decimals are off by 3. Divided by what? 20?
Divided by, no, 20 points. Okay. I don't know. I did a 20.1797 and then divide by 1,000 again.
No. Your math is off. You've divided more than you should by 1,000. You've done that somehow twice. Because you're off by 3 decimals.
Oh, it should be 606.9.
It has to do with how you're putting it into the calculator. You are using your EE button, right?
No, I divided by 1,000 directly.
You divided what by 1,000?
Multiply by 298 divided by 20.1797 divided by 1,000. That's what I did.
Yeah, but this is not. You're multiplying it by.
Gram, right? So I converted it into kg by
Yeah, but
multiplying
you're not converting it. This is 20.179 times 10 to the minus 3.
That's
It's divided by 1,000. But what you're doing is you're not saying this number divided by 1,000. You're saying the top number divided by 1,000 because you didn't put parentheses.
607.
If you use your EE button, you won't you won't have that problem.
Oh, yes.
You
This one divided
right? You said this one.
So that's what I did. Just divide by 1,000 is multiplication by
That-
10 to power minus 3.
I know, but that's not what you put in the calculator. You did not type that into the calculator.
Okay.
You want it to divide by 1,000, but you did not do that. Right here, you didn't do that. You didn't do that right there. Okay, you need to do that in here.
Multiply by
No,
multiply by.
you don't multiply it. You just say EE.
I did. Then
Do not multiply it. Take that multiplication off. Just say EE. There you go. Minus 3. 3.
because I really did not know how to use this. I never use
Yeah.
it's like syntax error. It's a syntax error.
Yeah, because somehow you got a syntax because somehow you were typing it in. Okay, did we get it? All right. What did you guys get for your What'd you get for your speed for neon? What did you get? 606, 607, 607 meter per second, right? Did everybody get 607? Awesome. And round to 607. Okay, so now let me ask you, which one of these gases is the fastest? Now, how are you going to determine that? How would you determine which of these gases is the fastest? How are you going to decide that? You got CH4, NO2, N2, and Kr, and they're all sitting at the same temperature. So you could calculate each one of these, but think about it. If they're all at the same temperature, then don't they all have the same T? Yes. And they all have the same R? Yes. And the 3. So what is it, the only thing that differs? The molar mass. Oh, but don't we know how molar mass and speed are related? Yeah, they're inversely related, aren't they? Yeah, so can't we look at that and look at the molar masses and decide based just on the molar masses? Yes, you can. Yeah, you can. Or you can calculate the temperature for all, the speed for all those. That's totally fine. Or you can think about it. The only difference is the molar masses, and the molar mass and the speed are inversely related. So which one of these is going to be the fastest? Methane, CH4? It's got like 4 hydrogen atoms in a carbon. Are you sure that this one's going to be it? And this one only has one of them. Kr is just only one atom. But the molar mass is what? Which one is bigger? Yeah, Kr is a lot bigger, right? So even though there's one atom, that's not the one that's going to go fastest. So you're right. Which one is the fastest then? CH4. That has the. Why'd you choose CH4? It has the lightest molar mass, right? The lighter the molar mass, the faster the particle. They're inversely related. Okay. Well, since we're talking about speed, then we can talk about things like effusion. What is effusion? That's evacuation, or into evacuated space. That's exiting through a tiny hole into evacuated space, because you don't want other molecules in here hindering their progress. So this is effusion. You think of the E word, effusion, exiting, evacuated space. It's going through a tiny hole. So the faster the particle, the faster we can move through there, right? That makes sense. Okay, that's effusion. And then we also have diffusion. That, instead of going into evacuated space, we're going through, dispersing through a bunch of other molecules, or in other words, we're making a mixture. Okay, so that's what diffusion is. So effusion and diffusion, when we sprayed the air freshener, which one was that one? That was diffusion. Okay, so does everybody see the differences between those two? Okay, now we're going to take our speed and we're going to do some calculation with Graham's law, which has to do with speed, okay, and our mass. Now, how do we say speed and mass were related? They were inversely. Does everybody remember that? Okay, so let's compare two gases. So let's compare two gases, and we know that molar mass is inversely related to speed, and we can think of our root mean square speed equation. So if I have gas 1 and gas 2, I'm going to compare those two rates. Now we said, think about our root mean square speed. The two gases are going to be at the same temperature, so isn't the 3 the same, the R the same, and the T the same? So the only difference is the molar masses, right? And aren't the molar mass and the speed inversely related? Okay, so I can do that. So I'm going to put my square root sign. R1 is the rate of gas 1. So where does molar mass go? On the bottom. Molar mass 1. And if R2 is on the bottom, then what? Where does molar mass 2 go? On the top, right? Okay, that's inversely related. Now, since there is no R here, we don't need to worry about changing it to kilograms per mole. We can just use regular molar mass. Okay, and the units will cancel. So this is one formula. This is Graham's law. So if we are comparing the two rates, we can compare the molar mass. That's kind of what we were doing when we had our list of gases over here, but now we can actually calculate some rates. So remember, it's inversely related. R1 is going to be on top. That means molar mass 1 has to be on the bottom. We don't want to mix those up, right? And then we've got R2 on the bottom, and we want molar mass 2 on the top. Okay, this is Graham's law. Now let's do another version of Graham's law, and let's think about rate and time. Now, the slower you're going, it's rush hour, those highways are packed, we're going really slow. What happens to my time? It gets longer, right? So the slower the speed, what? The longer the time. Okay. And then if I'm going really, really fast, high speed, what happens to my time? It's shorter, right? So are those directly or inversely? Well, which one now? Let's think. Directly or inversely? The bigger my speed, the shorter the time, right? Right? Is that right? Okay, inversely, yeah? Okay, so let's put that up here. R1 over R2 again is equal to, wouldn't this be what? If they're inversely, what am I going to put up here for time? T2, right? Inversely, T2. And then if this is R1, T1 here. Okay. Well, if R1 over R2 equals T2 over T1, can I put this in right here to my Graham's law? Sure I can. So let's rewrite that. That is equal to the molar mass of 2 over the molar mass of 1. All right, so let's look what happens. T2 is on top. Where is molar mass 2? On top. This is T1 on the bottom. Guess where molar mass 1 is? On the bottom. So these are going to be directly related, right? Okay, so these are your two laws. Here's this one. Remember, rate and molar mass are inversely related, but here's another one. Time and molar mass end up being directly related. Do we see that? Okay, so those are my two equations that I can use to do these calculations. So here's one. The rate of effusion of O2 is 484 meters per second. What is the rate of effusion of nitrogen gas under the same conditions? Okay, now we have a rate. You guys know what rate is, right? You know what the units of rate are. Okay, and don't be thinking ideal gas law here. Okay, that's not going to work, even though we have temperature and pressure. Those are just the conditions. Okay, we don't ever have a rate in the ideal gas law, so we're not going to use that one. We're going to use Graham's law, okay, of effusion here. So what is the rate of the effusion of nitrogen gas under the same conditions? All right, so set up your R1, R2, make a table. Make a table again. Okay, R1, what is it? R2, what is it? Molar mass 1, molar mass 2. Set this up, and then solve for the missing one. Okay, and you know what the molar mass of oxygen is, right? O2, what is that? It's 32. Yeah, how about nitrogen? What's the molar mass of nitrogen? Nitrogen gas. That's a diatomic, so it's going to be 28, right? Does everybody remember their diatomics? Yes? Yeah, because if you don't remember your diatomics, you could have put 14. That would not be right. All right, see if you can calculate that one. So you don't need to change the molar masses to kilograms. Just get the molar mass in the periodic table. But remember about the diatomics. Oxygen's 32. Nitrogen gas will be 28. Oxygen gas is 32. Let's see. Okay, so we put it in the equation. You divided it out, right? Divide it out first. Take the square root. You're watching your algebra there. Okay, so here's your table, right? R1, R2, M1, M2. There's no temperature here. You don't need to do anything with temperature or pressure, nothing. There's just extra numbers in here to make the problem true, but we don't need that in our calculations. Do you see that? Okay, so then you're just going to write down R1. Which one is oxygen? Is R1 oxygen? Is that what you decided? That's going to be oxygen. You might want to write that out here so you can remember that. And this one's going to be the N2. Okay, so what's the rate of oxygen gas? The rate of oxygen is what is the rate of the nitrogen gas? So that's a question mark for nitrogen. What's the molar mass of oxygen? What's the molar mass for nitrogen? Okay, so you have to think first. Think, what am I doing? You're doing this equation and that table. There is no temperature. There is no pressure. You see? Now, write that equation down and put the numbers in. This is back to that algebra thing again. So R1, which is 484 divided by your R2, which we don't know, equals square root, right? Molar mass 2. No. Molar mass 2 goes on top. Molar mass 2, that's this one. Be careful that you get the right one. Molar mass 2 over molar mass 1. 32 on the bottom. Don't forget your square root sign. I would do square root of the whole thing. Okay? And then you're solving for x. That's your x. Okay? You're solving for that. So divide those out and take the square root of that and then solve for x. Okay, did we get that? Be careful when you're doing your algebra. Okay.
So, do we need
to make it true? That speed will not be true if that temperature and pressure is changed. It's only true because it's at 27 degrees in 1 atmosphere. So I have to state that. Right? Got to be true. So, but I don't need to use it. Those are just the conditions. This is the equation that you're using, this one. So write these variables down and put that information in. So R1, you know what that would be. R2, you know what that would be. Molar mass 1, molar mass 2. Fill it in and then solve for the missing one. Yeah? Okay, so we know that the oxygen gas is 484 meters per second, right? And that's going to be 32, right? And this we don't know, and that's 28. So here's your variables. So the first thing you want to do in these problems is think of the equation that you want to use. Whatever equation you want to use, then get your variables and put them in. You're not going to use that temperature and pressure, are you? No. Okay, so did you plug it in? Yeah. What did you get for your answer? 517. Very good. So 517 meters per second is the answer to that equation. That's the speed of the nitrogen gas. Well, doesn't that make sense, though? Which is heavier, nitrogen or oxygen? Oxygen. So it should be moving slower, and it is slower, right? Okay, so we're going in the right direction. Okay, here's another one. Let's do the next one. Look at this. It says a sample of neon gas diffused through a pinhole and took 38 seconds. So 38 seconds. Is that a time or a rate? A time. Okay. So you know which equation you want to use, right? Again, start with the equation that you want to use, then list out your variables and fill it in and solve. Okay, so solve this one. Okay, how we doing over here? Everybody got it? We're all good? Easy? How are you doing? Easy? You're like, yes. Okay, awesome. Okay, how are we doing over here? Maya, did you get it? Okay, you're using the second equation, T2 over T1, right?
I did equation number 2.
Oh, okay. Yeah, I'll do that one on the board. That one's a little bit different. Do you have a question? Okay.
The time.
Did you solve for time? 77?
317.
77. T2
So we were
over
right
38.
About it was the molar mass for what is it?
For neon, it's always a gas.
For this one is
Neon is 20.2. That's neon. And krypton is 83.8. What? Yeah. Right? You got the molar mass. These are not diatomics. They're noble gases. They
stay the
don't.
same.
Right? They're nobility. They don't want to act with anybody else. But these are all diatomics. Yeah. Right? Okay. 77. No. Watch your math. No. You rearranged your. You rearranged your variables. You have to be careful how you do that, okay? Okay, so what is your answer for time T2? T2 is 77.4 seconds. Did everybody get that one? Okay, watch your algebra on this. Don't be careful that you didn't multiply by it when you should have divided by it. Be careful in rearranging those variables. That's probably the biggest mistake. Just be very careful. Okay, so do we have any questions about the 77 seconds? So we got that okay? All right, we're good? Okay, so watch that rearranging. That one, I'm going to show you how to do that one. Okay, so that second problem, let's talk about that one. Yeah. Okay. We can do this one. We can do that one. This one is a little different. This one's a little trickier. So let's talk about how we're going to solve this one. For one, there is no time in here, and there is no rate. So we're thinking, wait a minute, how am I going to do this? Instead, they give us something else. They give us the ratio. So we're going to use this as the ratio. So what they're giving to us is this ratio already divided out. Now the key part is, how do we know which gases are 1 and which gases are 2? Because if you reverse those, that's where you're going to get trouble. So the easiest way to do this is to read the sentence and then translate that to algebra. So let's do that. A sample of unknown gas effuses at a rate. All right, so let's write that down. Rate of unknown gas. Okay, so we would say rate of unknown gas equals, because it says rate of unknown gas is means equals, so write a little equals above the is, 0.462, so equals 0.462, and then what does it say? Times, okay, that's multiplication, so times what? Rate of nitrogen. So this is how you would write it. Just read the sentence and translate that into algebra. Rate of nitrogen gas, okay, is, that means equal, 0.462 times, that's multiplied by rate of nitrogen gas. Does everybody see that? Now, get the rates over onto one side. So to do that, that would be rate of the unknown divided by rate of the nitrogen gas is equal to 0.462. Rate of the unknown divided by rate of the nitrogen gas is equal to 0.462. Now you know which molar mass has to go on top, because that's the important part. You don't want to reverse that. So, right, if nitrogen gas is on the bottom, if the rate of the nitrogen gas is here, then what molar mass do I put on top? The 28. Okay. And then rate of the unknown would be, that's the molar mass of the unknown, right? Okay, now do you know how to solve that? So let's work through the algebra. 0.462 is equal to the square root of 28.0 divided by the molar mass of the unknown. Can I just pull out the molar mass of the unknown? No, you cannot do that. Why not? It's under the square root. So how am I going to get rid of the square root? Square both sides. Exactly. So I square both sides. That equals to the 28 divided by the molar mass of the unknown. Now you multiply molar mass of the unknown times 0.462 squared is equal to 28. And then you would say molar mass of the unknown is equal to 28 divided by 0.462, and that, of course, is squared. Now, be careful about how you rearrange that. Some of you are not saying 28 divided by 0.462. You're switching this around, so be careful how you rearrange your variables. Step it out one step at a time. Okay? All right, so that's how you would solve that problem. And the answer to that is 131 grams per mole. Okay, so that's how we solve that one. All right, that's working with Graham's law. Are you going to practice all three of those kinds of problems? Yes, of course you are. Okay, well, let's talk about, we've been talking about the ideal gas law, ideal gas law, ideal gas law. Well, what's an ideal gas? Well, we kind of talked about that in our kinetic molecular theory. Well, what's a real gas then? Well, a real gas is going to have a volume that's not negligible. A real gas is going to have attraction that occurs. Okay, so this is a real world, and real gases have that. So when does a real gas behave like an ideal gas, where volume is negligible and attraction is going to be negligible? When does that happen? Okay, so let's think about this. Temperature and pressure. When is it that the volume would be negligible? Under what conditions would the volume be negligible? Well, that means I have to have a large volume, right? Because if I have a little bitty small volume, then it matters about the volume of the particles. If I have a large volume, then those little teeny particles, its volume is negligible, right? Well, to have a large volume, don't I have to have low pressure? Because what happens under high pressure? Volume decreases. So under low pressure, then the particles are far apart, and so the volume of the particles can be negligible. But under high pressure, when you start squishing together, then the particle sizes start to matter. Not only that, but attraction starts to happen because you're putting them closer and closer together. So if they're attracted, then they don't hit the wall quite as hard as before, and so that affects the pressure. So you won't get true readings. So, what kind of pressure do gases behave ideally? What did we say? Gases behave ideally under? No, not standard. What did we say? High pressure or low pressure? Okay, let's go again. Volume of an ideal gas is negligible. What does that mean? It barely matters, right? Volume barely matters. When does volume barely matter? Big container or small container? Big container, and volume doesn't matter. If I have 10 gas particles in a big container, they're not going to take up much space, are they? What if I had those same 10 particles in a little teeny bitty volume? Is it going to matter? Yes. So you need big volume, right? So when do we have big volume? High pressure or low pressure? Low pressure. So when do gases behave ideally? Under low pressure. Yeah, it's like, which is a high or low pressure? Okay, gases behave ideally under which kind of pressure?
Low pressure.
Low pressure. Does everybody see why?
Yes.
Yes, low pressure. Okay, awesome. All right. Let's see. Let's talk about this graph right here. We said what kind of pressure? We said low pressure, right? Okay, here's argon. Here's an ideal gas. So at high pressures, we're not like an ideal gas. But guess what happens as we get closer and closer to low pressure? we start to behave like an ideal gas. Do we see that? Okay, well now let's talk about temperature. Okay, let's talk about temperature. Well, we said that the attraction between the particles is negligible, right? Okay, so think about our two magnets. If those magnets are moving slowly past each other, aren't they going to be pretty attracted? Well, what if those magnets were moving really fast? Not so much. Okay, so at fast, what does that mean about the temperature? Hot, right? High temperature, we're moving fast, right? So gases behave ideally at which temperature? High temperature! Yay! Okay, awesome, we got that. All right, now you can see what happens. You can see what happens as we get closer and closer to high temperature, right? Doesn't the gas start to behave like an ideal gas under high temperature? Okay, so those are the conditions of when gases in our world act like an ideal gas under those conditions of pressure and temperature. Great. Well, what if we don't have those pressures? What if we don't have that kind of temperature and that kind of pressure? Now what? Well, it's not an ideal gas anymore. Great. What are we going to do? We can't use the ideal gas law. Well, this is what we use. It's very similar to that. It is the ideal gas law. Does everybody see how it's PV equals nRT? Yeah. Yeah, that's PV equals nRT, but we have to take into account volume, and we have to take into account the attractions. So this is the van der Waals equation. Those A and B are constants that you look up for that gas, and then you plug it in here, and we do that calculations. Okay, so we're just going to learn about it and what the van der Waals equation is and why we would need that, but we're not going to actually do calculations with those. Yeah. You know, we used to do that calculation in the gas law lab. Oh my gosh, it took everybody like about an hour just to do this calculation. So we're like, okay, we're not going to do that.
Or did we give up?
Yeah. So
That standard's a bit lower.
yeah. Okay, so we're just going to learn about it, okay? All right. Okay, that finishes up chapter 10. Whoo!